In this lecture, we're going to discuss cylindrical coordinates, which is one way of extending polar coordinates to 3 dimensions. When you have a point in 3-dimensional space, say the point x, y, z, if we take its shadow down in the xy plane, we get the point x, y, 0. And we've seen that for points in the xy plane, it's also possible to describe their position using polar coordinates, where r is the distance from that point to the origin, and where theta is the angle that that ray makes with the positive x-axis. Cylindrical coordinates just uses r and theta, but also this third coordinate of z. And so it's governed by the same equations as polar coordinates, that x is r times cosine of theta, and y is r times sine of theta, and also that x squared plus y squared equals r squared. Now in cylindrical coordinates, you can start to look at equations of surfaces, things like, say, z equals r squared. So let's graph this surface, which again means I want to show all the points in 3 dimensions that satisfy this equation here. And a useful way to deal with an equation like this is to think about the intersection with, say, the yz plane. Well, the yz plane is just the plane x equals 0. You see, when x is 0, that implies that r squared is y squared, so in fact r is plus or minus y. So that means that in this case, z equals r squared becomes z equals y squared. So the surface that we're dealing with intersects the yz plane in the parabola z equals y squared. And for a similar reason, if I take the intersection of z equals r squared with the plane y equals 0, then I get the parabola z equals x squared in the xz plane. So that's the parabola that kind of starts at the origin, comes out in front, and then over here and back. So that's z equals x squared. And now what happens is essentially you're going to get a surface that consists of this curve rotated around the z-axis. So this is just the paraboloid that we've seen. I mean, of course, we sort of already know that because if z equals r squared and r squared is x squared plus y squared, this is just the equation z equals x squared plus y squared. So we've seen that already before. But the idea that we used here works for any such surface. If z is a function of r, then its intersection with the xy plane, with the yz plane, will just be z equals that function of y, and the intersection with the xz plane will be z equals that function of x. Okay, and we'll see that for some surfaces and solids, anything that has sort of an axis of symmetry, that cylindrical coordinates is a really convenient way of representing that.